And welcome back to Anton Math. Now in the last video we just stopped talking about the natural numbers and the integers, and in this video I'm going to talk about a new type of numbers called the rationals. Now what we mean by rationals is the rational numbers are the set of all numbers that are fractions that have non-zero denominators. Now we usually denote this with a big capital Q, and with a double bar notation that I've been using, we'll have some kind of double bar Q, or some books will have a little extra bar on the outsides and things. But this big Q means the set of all rational numbers. And the way that we define that in set notation is, before I talked about in this first little part, I want to give kind of an example of what a general element's going to look like. So rational numbers are all fractions. So I'm going to give an example. This is going to be a fraction, and I have some restrictions here. Right? When we talk about a rational number, we don't talk about, what if A is a fraction and B is a fraction? That's not necessarily what we're talking about. Or what if A is this, infinite decimal number? That's not what we mean. When we talk about a rational number, we talk about this fraction where both A and B are integers. Right? We need both A and B to be in the set of all integers. And we need an additional restriction on B as well. We need B to not be equal to 0. And this is very important. Let's look at why this is important. Let's just say that I have a b that's equal to 0. For example, let's look at the fraction 2 over 0, and that's equal to some number x. I want to look a little closely. What is that? What is x? Right? So this is the same thing. What I've written here, and what this symbol means is the same thing as, right? Or this is an equivalent statement to 2 equals 0 times x. Now what number can you think of where if you multiply that number by 0, you get 2? I can't think of a single one, right? We don't have such a number. Those numbers don't exist. So this is undefined, right? Or we write DNE. Does not exist. So we need that restriction. We don't just want b to be an integer. We need b to not be equal to 0 in order for these rational numbers to be well defined, right? We want all of these to actually be something. And we don't want to get we don't want anything in this set that is undefined. Now, I want to look at a special case of these. What if I have this set A over B, where A is in the integers, and B is equal to 1? Right? We notice this is a subset of the rationals, isn't it? This is a fraction. A and B are both integers. B is not equal to 0, but I'm getting a little bit more specific here. B is equal to 1. So this is the same thing as A over 1, such that A is in the integers, isn't it? Well, this is the same thing as, A over 1 is just A, so I write this as A such that A is in the integers. Right, so this is an important result. Look at this. This is just a special case of rational numbers is equal to all A such that A is in an integer. Well, we have a name for that. That's just the set of all integers, isn't it? So our conclusion for this little line here, well, the integers must be a subset of the rationals. Right? So all integers are also rational numbers. Now it doesn't go the other way around. Remember, not all rational numbers are integers, because we know that 1/2, for example, is a rational number, but 1/2, and we use this kind of vertical slash to say is not, 1/2 is not in the integers. All right, so remember this subset notation really just goes in one direction. Right? Now, it's important to note that we have infinitely many ways to denote all these rationals. We talk about 1/2 is in the rationals. We note that 1/2 is equal to 2/4 is equal to 17/34, etc. Right? We have an infinite number of ways of representing each rational number. But usually, when we're working with rationals, we're going to assume that they're in a reduced form. And when we get into methods of proof and doing some proofs later, especially proving whether a number is rational or irrational, it's going to be important to state those assumptions. It's very convenient to work with rational numbers that are reduced. And because these are all equal, we're always able to do that. Now with the representation I have up here with the rationals, if we start plugging in every a and b that are in the integers, we get a lot of repetition. But these rationals are just all of those distinct rational numbers, right? If I were to list out all the rationals, I wouldn't list out 1/2 and 2/4 and 17/34. I just list out 1/2. And we're going to want to work with those reduced numbers, right? Simplest is the best, right? The KISS principle, if you haven't looked that up. So that's going to be our convention. And like I said, we'll get more into that once, more into repeating elements in a set once we get more into the set theory section. But I want to note one more thing about rationals is rationals can also be written in decimal form. And it's very easy to spot out which decimals are also rationals. So in decimal form, terminating and repeating decimals are rational numbers. And in the next video, I'll address the one exception to this, right? We have terminating and repeating, so the only other type of decimal we have is non-terminating and non-repeating, right? It's an infinite decimal that never repeats. And that's what we're going to call an irrational number, right? And we'll talk more about that in the next video. But let me give some examples. First, terminating. Let's just say we have this terminating decimal. That means it eventually stops. And this is, easy to see. Say I have like, 3, 1, 4, 2, 7. I could keep going as long as I want, as long as it terminates. Well, this is very easily, I can just multiply this by 100,000 on the top and the bottom. It's very easy to see that this is just 31,427 over 100,000, isn't it? So here we've met our requirements. This is definitely a rational number, right? I have a as an integer, b as an integer, b is not equal to 0. That's all we need. So this is a rational number. Now it's not so clear right away that repeating decimals are rational numbers. Let's just say I have this number 3.17, and that 17 is repeating. Right, and I want to show that this is a rational number, and I'll show you how to find the fractional representation of this, and this is going to work every time, this kind of process. First, I'm going to set this equal to x. Right, let's just say that I have some number x, and it's equal to this 3.17 repeating, and I want to find out what the decimal representation is. Well, first I want to note that this is the same as saying x is equal to 3 plus 0.17. where 17 is repeating, isn't it? Or in other words, x minus 3 is equal to 0.17 repeating. Okay. So now I want to manipulate this so I can try to figure out what x is. And the way that I'm going to do that is I'm going to pull out, however big the repeating is, I'm going to multiply both sides by something so that I pull out the first set of repeating digits. Now in this case, my repetition is 2 digits long. So I'm going to multiply both sides by 100, and I get 100 times my whole left side, x minus 3, is equal to 100 times this 0.17 repeating. Well, that's the same thing as 17.17 repeating, isn't it? I've just taken the first, set of repeating values, I've put it over to the left of the decimal, and I have this, and that's the same as 17 plus 0.17 repeating. Okay. So let's take a look at this. I have 100 x minus 3 is equal to 17 plus, now I already found out that 0.17 repeating, that's x minus 3, isn't it? So I'm going to substitute from here. I'm going to substitute that down here. So this is the same as 17 plus x minus 3. Okay. Now I'm going to subtract this x minus 3 to the other side, and I get 99 times x minus 3 is equal to 17. Well, now I have this equation in x. I don't have any more repeating decimals. So from here we can, very quickly solve for what x is as a fraction, can't we? Expanding out the left side, I get 99x minus 3 times 99, so that's going to be minus 297, is equal to 17. And I'll add 297 to both sides. I get 99x. 297 plus 17, that's 314. And so I get x is equal to 314 over 99. There we go. And we can do this process with any repeating decimal. And you go ahead and plug that into your calculator. Plug in 314 divided by 99, and your calculator is going to spit out 3.17171717, and eventually it's going to say 2, because your calculator is going to want to round up. It doesn't show you repeating numbers forever, doesn't it? Now this process leads me into one more little result I want to note before we end this video. And we'll write this as a theorem. 0.9 repeating equals 1. 0.9 repeating equals 1. It's a very interesting theorem. And the first time you see this, you kind of reject it, don't you? You see this, well, no, it's not quite equal to 1. It's just 0.99, and those 9s keep going forever. That's not equal to 1. Well, for those of you who have taken calculus and know the basic properties of limits, you can kind of think of this as a limit in a certain sense, right? For each 9 that I write down, infinitely many 9s, I just keep writing 9s, 9s, 9s. That's kind of the same thing as the limit approaching 1 from the left, isn't it? But I'm not going to leave it at that. I'm going to give you a very simple proof here, and it kind of follows the same principle as that last example. So 0.9, let's say x is equal to 0.9 repeating. Well, following what we did before, that means that 10x is going to be equal to 9.9 repeating, right? So that's the same as 9 plus 0.9 repeating. But 0.9 repeating is just x. So I have 10x equals 9 plus x. I can subtract x from both sides. I'm going to get 9x equals 9. Dividing by 9 gives me x equals 1. There we go. There's no arguing with that algebra, is there? So 0.9 repeating is actually equal to 1. And like I said, this is, kind of resembles a limit. Now, it doesn't stop there. We can apply this with any repeating 9s. It doesn't just need to be 0.9. For example, let's say 0.529 repeating, that's equal to 0.53. 19.9 repeating, that's equal to 20. I can list more examples, but I think you get the idea. And I've gone a little long in this video, so that's it for rational numbers. In the next video, I'm going to talk about irrational numbers and the real numbers. So we'll see you there.